Hello, everybody. This is our second lecture on ultrasound, and we'll get right into it. So let's look at the objectives for today. After today's lecture, students will be able to describe the properties of an ultrasound beam, including the near zone, far zone, and also the focal zone. Also, students will be able to identify different approaches to multi-transducer arrays and the advantages of each. We should be able to name three modes of ultrasound imaging, the A mode, B mode, and also M mode. And then students will be able to determine the time required to obtain an ultrasound echo pulse and also define pulse repetition frequency. Students will also be able to name the main components of an ultrasound imaging system. Let's start by looking at ultrasound beam properties. Sound coming from ultrasound transducers produces a wavefront that radiates away from the transducer. If the source of ultrasound is a point, the wavefront is spherical, and if the source is a two-dimensional extended source, the wavefront is planar. Because multi-frequency transducers are commonly used in imaging, the ultrasound source may be considered a collection of point sources, each radiating a spherical wavelength into the medium, as shown on the bottom image on this slide. Because of constructive and destructive interference, there is a characteristic pattern to the sound waves produced. This is shown in the image below. When ultrasound propagates from a surface, the beam can diverge as it travels through the medium. For a single crystal transducer, the shape of the beam has certain characteristics that can be identified. There is a near field, a far field, and a focal zone. The near field is also called the Fresnel zone, and the far field is the Fraunhofer zone. The beam converges to the focal zone and diverges after the focal zone, as the image below shows. For an unfocused single element circular transducer, the distance of the near field is determined by the transducer diameter and the wavelength of the transmitted sound. A single transducer element is shown with the focal distance also shown. So this is the far field, the near field, and this area will be a focal zone. In the near field, the beam converges because of multiple constructive and destructive interference patterns of the ultrasound waves from the transducer surface. The near field is closest to the transducer face, and the beam diameter converges to approximately half the transducer diameter at the end of the near field and begins to diverge after the near field. The near field length is dependent on the transducer diameter and propagation wavelength or frequency, as the formula below shows. And I'll point this formula out to you. So here is your near field length in soft tissue, and it depends on the diameter of the transducer and frequency. And remember that frequency and wavelength are also related. The far field is also known as the Fraunhofer zone, and the beam diverges in this region. For a large area single element transducer, the angle of ultrasound beam divergence for the far field is given by the formula shown here, where d is the effective diameter of the transducer and lambda is the wavelength. So I can show you here with a laser pointer. This is the effective diameter and that is the wavelength, and the angle theta is shown here for the far field. The focal zone is the region between the near field and far field. The ultrasound beam is the narrowest in this region, and it is the best region for lateral resolution. For single element transducers, scanning of the patient may be accomplished by physical motion of the ultrasound transducers. The sonographer can sweep the transducer back and forth manually, or a mechanical or automatic system may be used. Several methods for mechanical scanning are shown in the figure on this slide. The scanning technique that uses an automatic scanning mechanism for the transducer is referred to as mechanical sector scanning and is shown on this image, which is the top left image. And the other scanning methods involve reflecting the ultrasound beam off an oscillating mirror, as in the bottom image C, or using a single transducer oscillating at high frequency, as in this top right image B. For multi-crystal or multi-element transducers, scanning is achieved electronically, as we shall see next. Instead of manually sweeping the ultrasound transducers to change the direction of the beam, the ultrasound beam can be swept back and forth by changing the timing excitation of the crystals. This is done for transducer arrays of multiple crystals shown on this slide. Transducer arrays may be made of a linear array of crystal elements or a curved array of crystal elements. Linear arrays are shown on this slide. For electronic sweeping, crystal elements in the array are excited in groups of between 3 to 20 each time. Each excitation of a group results in one scan line. For the next scan line, the succeeding group is chosen to overlap the first group and excited. This forms the second scan line. In the image shown, the first group is numbered 1, 2, and 3, and the second group is 2, 3, and 4. This pulsing scheme is called a linear switched array. By sequentially exciting the entire array, an image composed of typically 64, 128, 256, or 512 scan lines can be obtained. Another method for scanning with a linear array uses phased array technology. In a linear phased array, all elements of the array are used to obtain each scan line. This is typically about 128 elements. By using slight delays between excitations of the elements, the beam may be swept to the left or right as this top image shows. A variation in the time delay scheme in a phased array may also be used to focus the beam at various distances throughout each image as shown in this bottom image. This is called dynamic focusing. We shall learn more about this in the next slides. Another type of array, the annular array, can focus in all planes perpendicular to the axis of the beam. The annular array shown on this image consists of a series of piezoelectric elements arranged in concentric rings. The beam may be focused at various distances from the transducer phase by varying the time delays among excitations of the rings. A linear array is also shown on this slide to the right. Ultrasound transducers are designed to both transmit and receive ultrasound signals. For multiple frequency transducers, the transmit focal zone is achieved by simultaneously firing transducers in a pre-programmed pattern. Multiple focal zones can be produced by varying the phase timing of the transducer array elements. Focal distance is a function of the transducer diameter, the center operating frequency, and the presence of any acoustic lenses at the transducer element surface. The focal distance is shown on this image with the focal zone length shown also. And in both phased array and linear array transducers, focal distance is selected by applying specific timing delays between transducer elements, causing the beam to converge at a particular point. During the receive mode, echoes arriving at each transducer element from some depth in tissue are summed together in the phased array mode. Because the echoes from a point in tissue travel different distances when they arrive at each transducer element phase, echoes arriving at the edge of the transducer travel longer distances than echoes arriving at the center of the transducer. So signals from each transducer element must be rephased to avoid resolution loss. One way to accomplish this is to rephase the signals by introducing delays in a method called dynamic receive focusing. Delays from shallow depth are longer than those from deeper areas because at deeper regions there is little difference in the signal. The image on the slide shows delays and focus from different depths as pointed out. So from a shallow depth, the distances between the edge travel distance and the center travel distance are significant compared to echoes returning from deeper areas where this difference between this distance and this distance is not as pronounced as this. Transducer arrays employ the technique of a dynamic aperture, in which the diameter of the sensitive region of the array is expanded as signals are received from greater depths. This technique maintains a constant lateral resolution with depth. As part of the primary ultrasound beam, there are small beams of greatly reduced intensity that are emitted at angles to the primary beam. These small beams are called side lobes, and are caused by vibratory modes of the transducer in the transverse plane. Side lobes can produce image artifacts in regions near the transducer if a particularly echogenic material such as a biopsy needle is present. Side lobes are shown on the image on this slide, as you can see. For multi-energy transducers, because the transducer surface is not continuous or smooth, it acts like a grating to the ultrasound beam produced. The effect is that some of the ultrasound beams are emitted off-axis. These ultrasound beams are called grating lobes and can result in appearance of highly reflective objects in the main beam. So grating lobes are shown here on this image. And the main ultrasound beam is shown, and here are some side lobes. So from the preceding slides, we can say that multiple transducer arrays provide several advantages. First, they provide electronic beam steering. Second, they permit dynamic focusing and beam shaping. Let's now look at resolution in ultrasound. We shall start with axial resolution. Axial resolution is the resolution along the axis of the beam. It depends on the spatial pulse length and it's independent of depth. Axial resolution is equal to half the spatial pulse length. The spatial pulse length is equal to the number of cycles multiplied by wavelength. Higher frequencies have shorter wavelengths and so produce better axial resolutions, but are less penetrating because of the higher attenuation coefficients at higher frequencies. So on this slide, if you look at the image up here, lateral resolution is shown as the resolution in this direction of the beam. Axial resolution is along this direction of the beam, and elevational resolution, which we shall talk about later, is along this face of the beam. So it's along the thickness face of the beam. So this portion of the beam is your elevational resolution. And so you can see here that in the narrow portion of the beam, elevational resolution will be better. And also as the beam curves this way in the lateral direction, the lateral resolution is better at this location. We will talk more about this as we go down in the other slides. Lateral resolution is defined as resolution in a direction perpendicular to the axis of the ultrasound beam. Lateral resolution depends on beam diameter and depth because it is best at the near field, far field interface. For circular single transducer elements, the location of the focal zone depth depends on the diameter of the transducer and frequency or wavelength of the beam. For multi-frequency transducers shown on this slide, the lateral resolution is also best at the focal zone shown because the beam is narrowest at that location. Beam steering is used to produce multiple focal zones as shown on the bottom image on this slide. So in this location here, beam steering will produce multiple focal zones. So you can have about 4 focal zones as shown here or even more depending upon beam steering. Lateral resolution is shown here where in this region here where the beam is narrowest, the resolution is best. And you can see that the structures away from that focal zone are more smeared out, meaning they have lower resolution. Elevational resolution is along the thickness direction of the transducer as shown in this figure. So this is the thickness direction. Elevational resolution depends on the thickness of the transducer face. That is the number of rows of transducer elements that are in the transducer. So more transducer elements means a lower elevational resolution, and fewer rows of transducer elements means a better elevational resolution. With phased timing delays, multiple elevational zones can be produced as shown on this bottom image here. So you can have multiple focal zones as shown below. Generally, ultrasound images are formed using a pulsed echo mode. The pulsed echo mode requires the use of various instruments listed on this slide. We shall learn about each of these devices on the next few slides. The first instrument we shall learn about is the beamformer. The beamformer generates timing signals in a pre-programmed pattern to focus the beam and to steer the beam in a phased array transducer. The next instrument is the pulsar. The pulsar or transmitter is responsible for generating the ultrasound pulse and transmitting it into the patient. In pulse echo operation, a pulse of 2 to 3 cycles long is sent out by the transmitter and the receiver listens for echoes. The time between transmitted pulse and the received echo is dependent on the depth of the returning echoes as shown by the formula on this slide. The echo time can be calculated by just multiplying 13 microseconds by the distance traveled or depth. The time between pulses is the pulse repetition period as shown here, and the number of pulses each second is called the pulse repetition frequency. Pulse duration is how long each pulse lasts. Typically, pulse duration is between 1 to 2 microseconds. The transmit-receive switch allows the ultrasound transducer to switch from transmit mode to receive mode to isolate the returning echoes from the transmitted echoes. The returning echoes range from 1 to 2 microvolts, so this will have to be amplified before they can be processed and displayed. When signals return from tissues, they are first preamplified and then sent to an analog to digital converter before being passed through to the time gain compensation circuit. In modern ultrasound systems with multiple transducer elements, this is all done in parallel. The typical analog to digital converter has a bit depth of between 8 to 12. After the returning echoes have gone through the analog to digital converter system, they are sent to the beamformer block as shown on this slide. Digital processing algorithms are used to focus and realign the returning signals to bring them into phase before the output is summed and sent to the next processing stage, the receiver. The bottom image shows a transducer with the preamplifiers, the ADC, beamformer stage all incorporated into a single head. After returning echoes are focused, rephased, and summed, they are sent to the receiver. The receiver takes the signals and processes them by performing gain adjustments, dynamic frequency tuning, logarithmic compression, rectification, demodulation, and envelope detection. If the signals are outside the prescribed envelope detection window, they are rejected before final image processing for display. The entire process is shown on the bottom image for this slide. The operator is in control of setting the time gain compensation and power levels and so on. Time gain compensation buttons are shown on the top left image here. So in a typical ultrasound, this will be your time gain compensation, and there are various buttons here for power settings and gain and so on. After the echoes are processed, they can be displayed. Let's look at some display modes. The first display mode is the A mode or amplitude mode. This is like the one-dimensional display you would normally see on an oscilloscope. A mode reveals the location of echo-producing structures only in the direction of the ultrasound beam. This figure shows the amplitude versus time plot of the signals on an oscilloscope display. This is typically what we call the amplitude mode, and that's shown here. So the structures you see here, A, B, and C, are just displayed here as spikes on the display. In B mode display, the signals are displayed in 2 dimensions. So rather than displaying amplitude as in A mode, the amplitudes are represented by the brightness value at the XY location. High amplitude echoes can be presented as either high brightness or low brightness to provide either white on black or black on white presentations. Most images are viewed as white on black, so high echo areas will appear bright on the display. B mode images can be displayed as either static or real-time images, and for real-time image display, images are displayed at greater than 24 frames per second, but will show some flicker. If displayed at greater than 48 frames per second, there is no visible flicker shown. And so on this image, this is your B mode display as shown here, and it shows you the structures being displayed here, and that is what it will look like on a B mode display. M mode presentation of ultrasound images is designed specifically to show moving structures. The most frequent application of M mode scanning is echocardiography, where the motion of various interfaces in the heart are shown graphically on a cathode ray tube or a chart recording. In modern systems, the images are digitized and displayed on a digital monitor. The images on this slide show the motion of structures in the heart. M mode display shows a periodic pattern of the motions as shown on this image up here. And you can also see here with the ultrasound beam striking the structure, striking the interfaces here, the display in M mode is shown as the motion structures this way. The last module on this slide is the scan converter. The function of the scan converter is to create 2D images from echo information. It includes a memory center for digital information. The memory center is configured as a matrix of small pixels that represents a rectangular coordinate display. There is also a digital interface, post-processing software, and storage. The final image is often recorded with a 512 by 512 by 8 bits per pixel uh, mode, and this represents about a quarter megabytes of data. For color display, the bit can be as much as 24 bits. So the image here shows the scan converter on this box. Let's finish up with a few questions. This is the first question of 3. Which of these is not an ultrasound scan mode? I will give you about 10 seconds to think about it, and then I will display the answer on the next frame. If you chose C mode, you'll be correct. The A mode is our amplitude mode, B mode is brightness mode, and M mode is motion mode. So we discussed this a few slides back. The correct choice here is C mode. This is not an ultrasound scan mode. This is the next question. Which of these is not true about ultrasound beam transducers? And I will give you a few seconds to look at it and then display the answer. The correct choice is the second choice. The best resolution is in the far zone. That is not true about ultrasound beam transducers. Remember, the far zone is the Fraunhofer zone. There is a lot of divergence of the beam in the far zone, and so the resolution is poorest in that zone, or at least it's going to be poor in that zone. The best resolution is in the focal zone. The last question is shown here. The ultrasound instrumentation that performs gain adjustments and dynamic frequency tuning, logarithmic compression, rectification, demodulation, and envelope detection is called what? And I'll give you a few seconds before we go on. The correct answer to this question is receiver. The receiver performs all those roles. The pulsar is a transmitter which produces a pulse and transmits an ultrasound signal. Preamplifiers preamplify the returning echo, and the beamformer shapes the beam and is able to steer the beam. So the correct choice is the receiver on this question. So this is the last question on this slide, and so this is the end of the lecture. Thank you for watching this presentation.